So we're going to continue our discussion of the part of this paper that is explaining to us an interpretation of the curvature scalar. We've already done its interpretation of the Ricci tensor, and we already know how to interpret the curvature tensor. So the curvature tensor gives us this. We understand this in terms of how volumes are moving around through space-time. And this likewise gives us a way of understanding R. Now, the problem is this was actually a pretty hard analysis from our lecture before last. This analysis is even harder, and to get to it, we need to understand Riemann Normal Coordinates, which we're going to talk about today. And we warmed up by talking about Fermi-Walker transport in our last lecture. So now let's get into this idea of Riemann normal coordinates, which is going to require us to talk a little bit about the Tetrad Formalism first, and we'll just take our time and we'll get through the whole thing. All right, so let's begin. So we begin, as usual, with our space-time. That's what this blank screen is. Because it's a space-time, we are presuming the existence of a metric. That's what a space-time means. It basically means you have a 4D manifold with a metric. So this space here is that's what this represents. And because it's a manifold, that's a fundamental assumption of general relativity. Because it's a manifold, we know that we can lay down a coordinate system on the manifold. All right, so now inside this coordinate system, we are going to introduce Alice, the owner of a laboratory. Now inside this coordinate system, I pick one point, and that's Alice's point. That's where Alice lives, right? Alice lives at that point. So what's going on at that point with Alice? Well, what Alice does at this point is she establishes a laboratory, right? So I'm going to erase this and give Alice a laboratory. That laboratory exists so small that, well, it's a small lab. We'll talk about what small means a little later. Essentially means geodesics leaving that lab don't cross inside the lab is sort of one way of looking at it, but we'll get to it a little more. So this is Alice's lab. So whose coordinate system is all of this, right? Well, coordinate systems don't belong to people, but it's our coordinate system. It's the meta-analyst's coordinate system. It's the bird's eye view coordinate system. It covers all of space-time and is totally arbitrary, right? And it's four-dimensional, right? So I'm going to label these x1 and these x2, and the time-like coordinate and this suppressed third spatial coordinate, they're out there also, right? So this coordinate system is established by our bird's eye view perspective, but not Alice necessarily. Alice lives in this little laboratory. So what is Alice going to do? Well, she wants a coordinate system that is orthonormal and simple to work with because she's running a lab. So our global coordinate system allows us to do something important at any point. We can, at any point in space-time, establish the tangent space, right? Which we call the tangent space. It's four-dimensional vector space. And it's got a coordinate basis, which I'll call partial mu, right? That's the coordinate basis located there. And that immediately gives us the coordinate cobasis, and we know it's a real I better maybe decrease my thickness. It's a real vector space. There, I cleaned it up a little bit. Actually, though, I got to be a little careful, right? This is the tangent space. The tangent space is a vector space, and this is the coordinate basis. This guy's not in the tangent space. This guy's in the cotangent space, right? So I really shouldn't put that in the box, right? If I wanted to, I could write another box, right? And then I could call this the cotangent space, which would have an asterisk there, and then it would have a basis dx mu, right? Okay. So I can do that anywhere in the space-time. In fact, I must. Every place in the space-time absolutely has this. If you have a coordinate system, you have a coordinate basis located everywhere in space-time, including in Alice's laboratory. So Alice's laboratory also has access to the coordinate basis. But this arbitrary coordinate system that covers this large patch of space-time, it's got a couple problems, right? For example, it's not necessarily, in fact, it's not even likely to be orthonormal, which means that G of partial mu partial nu, right? That certainly does not equal the Minkowski metric mu nu, right? Space-time, if it did, space-time would be flat right here in these coordinate system, right? But it's probably not, right? It's probably not that. What are the chances that this particular coordinate system at this particular point is the Minkowski metric, right? It's going to be some function of space-time, the components, right? So this, by the way, is defined as G mu nu, right? This is the components of the metric tensor as a function of space-time, right? X, say beta, right? In other words, the components of the metric tensor, I better say this correctly, the components of the metric tensor is a function of space-time. At any particular point in space-time, this metric has an operation that takes two vectors and gives a number. It's very unlikely that number is going to equal the Minkowski metric, right? Which means you're not expecting G00 to equal -1, G11 to equal 1, to equal G22 to equal G33, and then all the others to be 0. So you're not expecting it necessarily to be diagonal and orthonormal with respect to the Minkowski metric. So given this coordinate system, and even if it was, then the problem would just be transferred to Bob, right, who's over here, and he has a lab. And what are the chances that this coordinate system is flat here for Alice, and for Bob's lab over here, right? So this is a fundamental problem, and this is one of the reasons why Alice probably won't use the coordinate system laid out on the whole space-time. But what will she use? All right, so what would Alice do? So let's take a look and design our space-time again and start over and give Alice an orthonormal coordinate system. And the way we'll do that is we'll start with, just to keep us grounded in the work we've already done, this is going to be the bird's eye coordinate system. And this is a coordinate system that covers a large patch of space-time. It's got 4 coordinates, x0, x1, x2, and x3. I'm going to suppress x0 and x3, so this kind of should be laid out as a piece of space-time. That would be a spatial plane, right? But the point is it's supposed to be abstract coordinates, right? And we've decided that Alice's lab is located right here. And so what I'll do to demonstrate that is it's a little lab, right? Because we want her lab to not be so big that she can actually sort of detect obviously the curvature of space-time inside the lab itself. So there's her lab, and I'll put Alice right here to indicate this. This is her laboratory. So what is she going to do? Is she going to be likely to adopt these coordinates? And we'd think, no, probably not, because these coordinates aren't necessarily adapted to her lab. They're adapted to understanding perhaps the mathematical structure of the space-time, right? The metric itself might be well adapted to these coordinates, but they may not be good for regular routine experimental work. So what she would do is inside her lab, she's going to set up an orthonormal frame of coordinates. And I've drawn it right in here, right? It'll be an E0 basis vector, an E1 basis vector, and an E2 basis vector. And they will be orthonormal. So, and there's an E3, of course, but we suppress it. And it's very likely that if the lab is, say, free-falling, that this E0 basis vector, just like we did for the Fermi-Walker transport, will be established to be tangent to her world line. So this would be the equivalent of a clock, her internal clock just ticking away, and that the measurement off that clock, the proper time measurements off that clock, would be the coordinate position in E0. And E1 and E2 would be measured spatially, and we'll assume everything is in the same units, right? But these are 3 basis vectors that Alice is going to establish. So let's see if we can just step back and figure out exactly what all this means. I found it confusing when I first started learning about tetrads, right? She's establishing a little thing in here called a tetrad. And that tetrad is the basis vectors that she is going to use. So what do we remember from our old analysis of spacetime, or our standard analysis of spacetime, the assumptions of what spacetime is according to the theory? And we know it's a manifold, and at each point in the manifold we have a tangent space. And you remember how I used to mark off the tangent space. I used to symbolize it with a little box like this, right? I would say the tangent space's name is tangent space at the point P. If I guess I would have to call this the point P, right? And it was four-dimensional tangent space. Its basis system is the coordinate basis system. Oh, I got an X there. That shouldn't be an X. That should be a mu, right? Partial mu. So it's going to have a coordinate basis at that point, and it's a real vector space because in general relativity we just use real vector spaces. So every point in spacetime has such a thing, including the point where Alice is at, right? So Alice has a tangent space right here at her lab, and that tangent space contains vectors, and I should just take it's the exact same structure, right? So if I just pasted that structure right here, right, and attached it to her little point there, then it's the same thing, right? The tangent space exists regardless of whether she has a laboratory or not. And so at this point in space-time, at the center of her laboratory, she has access, or we, from the bird's eye view, certainly have a tangent space with a coordinate basis system. And she is going to use that same tangent space, but she's going to erect a different coordinate system. So this is now a question of how do we understand her basis vectors E0, E1, and E2, in terms of the coordinate basis vectors of the underlying coordinate system. And this is not a hard problem. However, it can be notationally quite a bear because there's a lot of subscripts going on. So let's take a good look at how we'll write this down. I'm going to push this all over like this, make it as big as I can. So let's take a look at her basis vector E0. Now, assuming her basis vector E0 it's whatever she chooses E0 to be. It's going to be time-like probably, but it is a vector in her tangent space. So E0 is an element of the tangent space at, I guess I should call this TA for Alice, right? Because it's her laboratory. So this will be the tangent space at the point A. So this is a vector that's an element of the tangent space of A. Ergo, E0 has got to be described as a set of components times the basis vectors that we use in our bird's eye view. Well, what are we going to call those components? Well, if the name of the vector is E0, right, indicating it is her zero vector, it's still a vector in the tangent space. It must be decomposable into these components. So this guy has to have its own components, which we are going to call E0 mu. So this is your standard Einstein sum, and this is the name, right? The name of the vector is this, and this is the space-time index, all right? So the space-time index is summed over, but there's a subscript in here that describes which of the tangent vectors, right? Which of the tangent vectors this is in Alice's lab, and it's her E0 tangent vector. So this subscript here ends up being part of the name of this object. So, you might be inclined to actually write it something like this, E0, where you literally attach it so you know that you're dealing with something that's part of the name. The problem is that it's part of the name, but it too will be summed over in a moment. But we do want to distinguish between these subscripts, which are the names of the tetrad subscripts. We'll call them the tetrad subscripts. We need to distinguish between the tetrad subscripts and the space-time indices, where the space-time indices go back to the sort of bird's eye view coordinate system. So how do we make that distinction? Well, different books do it different ways, but first let me finish writing out the rest of the basis vectors. So this is how we would, so far, write everything out. Each one of these basis vectors is expressed in terms of this basis. Now, the issue, though, is that what's worrying me is that these subscripts, these tetrad subscripts, are going to be confused with the spacetime subscripts. So that we've got to take care of. And the way we take care of that, typically, is we give the tetrad subscripts a little hat. So we would write E0 hat, like that. Or E1 hat, E2 hat, E3 hat. So we know that we're not referring to a space-time index. And notice that we chose to subscript the names of the tetrad basis. So the tetrad, we chose a subscript here as opposed to, say, E0 hat, right? And there's a good reason for that, right? The reason we're doing that is because it is a vector, right? We've decided that the actual basis vectors, the actual vectors are going to come subscripted in the tangent space. So basis vectors are subscripted, and the components of basis vectors are superscripted. This guy's meant to be a vector in this tangent space. Ergo, if it's going to have if it's not just something with a name like x, which is an element, say, it's a vector in the tangent space, which would be written just straight like this. If x's name does in fact have a subscript, we might as well subscript it low in order to remind us that it's a vector. It's an element of the tangent space. So we put these hats on it. The other thing we do is when we refer to this system, this tetrad system, we refer to it using a Latin letter in the subscript. So it would be E sub A, E sub B, E sub C. Those would refer to various elements, the element A, B, C of the tetrads. And I've also seen it where they throw the hats on those as well. So they're doubly redundant, right? It's Latin with a hat, right? So there's two reasons to be redundant. But when those Latin letters get converted into actual numbers, then the hat really helps us out because it distinguishes between the space-time indices and the tetrad indices. You can never sum space-time indices with tetrad indices. You can only sum space-time indices with other space-time indices. Okay, so then the other thing to keep in mind is this is a new basis, right? The E0 or the E basis, the tetrad basis, is a legitimate basis for the tangent space. Ergo, any arbitrary vector x, which is an element of the tangent space, x can always be written as x mu partial mu using the bird's eye coordinate system, but it's also can be written as x a, I guess, hat, e a hat, right? So the vector x has components in the bird's eye system, and it has components in the tetrad system. And any vector can be written either way. It's the same vector. It's simply a matter of the basis. So we need to sort of work through this a little bit just to get comfortable with it. This is diverting into a bit of a lecture about the Tetrad Formalism, and it's only an introduction to the Tetrad Formalism, but I am very concerned about the notation because I found the notation extremely confusing when I first learned about it. All right, so now we're looking at Alice's lab. Here's Alice's lab. She's set up this system of basis vectors in her tangent space, and the relationship of her basis vectors is this. Why do I have a 1 there? There should be no 1 there. So the relationship between her basis vectors, or her tetrad, and the bird's eye coordinate system is just given by these numbers here. These are numbers, right? These are like little matrices, right? This is a linear transformation. These little e's, this is a linear transformation between one basis and another. So this actually is a matrix. So the way you would actually write this, perhaps, is E a hat equals E a mu partial mu, and this is effectively a linear transformation. So we instead of writing it with the lambdas like we used to write it, we just use these e's because we're kind of indicating that this is a tetrad basis transformation. It's not going from one arbitrary basis system to another. Because why would she set up a tetrad system unless it was orthonormal? So how do we understand orthonormality now? That's the next sort of thing that Alice would do, is once she sets this up to be orthonormal. So what does that mean? Well, let's remember how the metric is understood in the context of our work. We recall that the metric components is the metric tensor operating on the basis system. And in our bird's eye view, which is what our metric is written in, this is the formula. This is the coordinate-free version, and then we put in these two particular vectors, which happen to be the coordinate basis vectors, and we end up with the components of G in this coordinate system. And then we would write down the full tensor, and the full tensor, as we've learned many times before, is a 0-2 tensor where the components, and this is the basis of the tensor product space. And so that's how we define G. So if you were orthonormal, if you were an orthonormal coordinate system, then it better be the case that these components end up equaling the Minkowski metric. So the way we would understand that is that the metric tensor, the coordinate-free metric tensor, taking in the two basis vectors of the tangent space. Remember, it takes any vectors in these slots, right? In this case, I threw in basis vectors, the coordinate basis vectors, fine. In this case, I threw in the tangent vector, or the tetrad basis vectors. That's fine. This is the coordinate-free object. It takes in any two vectors. What it gives out, we're going to call G A hat B hat. And because of the construction, we're going to design that to equal the Minkowski metric, which, as a reminder, basically equals -1, 1, 1, 1 on the diagonal, right? And the off-diagonal elements are 0. I guess that's the better way of writing it. Okay, so now let's plunge into this. So the first thing I'm going to do is I'm going to take this, and I'm going to turn it into G E A hat mu partial mu E B hat nu partial nu, right? Which by linearity equals E A hat mu E B hat nu times G of partial mu partial nu, which of course is going to equal G mu nu E A hat mu E B hat nu, which we're defining as G A hat B hat, right? And that's the relationship between the metric components from the bird's eye view with the metric components associated with the tetrad. So now I can always find the magnitude. I can now use this to raise and lower indices, tetrad indices, because now I have a way of saying, I can now write, I guess, G E A, well, let me do it this way. Undo G X A hat E A hat Y, I guess I would have to do B hat, right? Right, Y B hat E B hat, that is going to be X A hat Y B hat times what's left behind here, which is G, which is G of E A E B, which I've actually shown already, right? G E A E B is this guy, which is this guy here. So I just write G A hat B hat, and that allows me to find the magnitude between of X and Y using the metric, right? So I've created a metric that is adapted for the tetrad coordinates. And so now you can kind of get a little bit of the pitfalls here now we're summing, we're using Einstein sum over tetrad indices, right? Here's an Einstein sum over a tetrad industry. And here it's an Einstein sum over space-time indices that leave behind tetrad indices. So this is a bit tricky because in the beginning I said, oh, well, be careful, right? This is the name, right? E0 is the name of this vector, right? Instead of calling it x or y or z, we're calling it e sub 0, e sub 2, e sub 1. And as part of the name, it's not involved in the sum. However, the reason we give it a number is so we can exploit summation over tetrad indices. So tetrad indices can be summed over and spacetime indices can be summed over. And this is the connection that allows us to understand the metric in terms of the tetrad indices. The point is we have to design GAB, right? We have to design this thing so that G A hat B hat actually equals Minkowski A hat B hat, right? That's the point. So we are choosing these numbers, right? We choose these numbers. Where are those numbers? We choose these numbers here, right, in order to eliminate the off-diagonal elements of the metric. But it's only done at the point of the lab, right? It's only done at the point of the lab. Where she is right now, where Alice is sitting, she sets up her tetrad so that these numbers are such that all the off-diagonal elements of the metric go away as long as she's working in this particular basis. So that is a quick and dirty class about how these tetrads work. Now, in principle, I suppose we have the new problem that if you consider the bird's eye view in the lab is only at one place for 1 second, right? For 1 instant in time. So she's here now, but later she's going to be here or here or here. Or if she's, if we're in the rest frame of the lab, she's at least moving through time, right? So the lab is never still. So she has the same kind of problem that we had in the Fermi-Walker transport, right? Where she may want to just set up her E0 basis vector to be tangent to her world line, whatever it is, and then set up the other legs of her tetrad to be orthonormal to that and orthonormal to each other. But we can never really talk about the lab just standing still in space-time, because nothing stands still in space-time. Everything has a world line in space-time. So you might ask, well, why don't we just set up this verbane everywhere, right? Why don't we just put in every point in space-time, just set up, I call it a verbane. A verbane is, I think, one of my books used that word a long time ago. Tetrad is the word we want to use, right? It's the Tetrad Formalism. But why don't we just set up a little tetrad here, right? And here, and here. Why don't we set up a tetrad everywhere and just use the tetrad, orthonormal tetrad every place, and every place will now have a flat space metric. And, well, you certainly could, right? You certainly could at every point presume a laboratory exists and set up a flat space metric. The problem is that, let me give you an example, right? Well, let me sort of explain what this would mean. So you have an E0 vector here at A. Then here at this other point, you would also have an E0 vector, right? And it would be expressed in terms of the bird's eye metric differently, right? So you had have E0 hat mu partial mu all located at this point, which we'd call B. So I need another little index here for B. So say I put the B over here. And then this one would be A, right? Mu partial mu. And then here's one over here. And what will that be? Well, that'll be point C. So I have E, C, 0, mu, hat, partial mu. So every point in space-time, if you did this exercise, would end up with its own E0 vector, and likewise E1, E2, and E3. But let's just consider the E0 vectors. So every point in space-time has its own E0 vector, part of a tetrad that we built. The problem is that, so that suddenly becomes what? It becomes E0 hat as a function on spacetime, right? Where this is the coordinates of spacetime. We've basically created an E0 vector field, right? Everywhere in spacetime there's an E0 vector. So that is what an E0 vector field is. And this x mu would go through the points A, B, C, the coordinates of all these points. Well, the problem is if you did this, what you'd probably discover, except for the most simple of all spacetimes, you'd discover that this vector field is non-holonomic, which isn't a fundamental problem with a vector field. Most vector fields are non-holonomic. But what this means is it doesn't describe a coordinate system on the spacetime. It's an ambiguous coordinate system. If you go back to, I think, lesson 43, which I rewatched not long ago, and it's a long, slow, boring lesson. I'm really sorry, but it does explain this idea of a non-holonomic system. The point is you just can't flatten space-time everywhere using this technique, right? That just doesn't work. It would be too easy if you could. But you can flatten it at one point, and we're going to take advantage of that. But what we have done is we've established an orthonormal coordinate system at a point in space-time, right? And we've done it using the bird's eye system as well. For us, Alice just sort of sets it up as it is. And now we're going to broker that orthonormal coordinate system or that orthonormal basis system. I didn't say coordinate system. I should have said orthonormal basis system. Alice sets up an orthonormal basis system. We're going to broker that to create a coordinate system that works well nearby Alice, where she can now label all the points of space-time that are near her, right, in any direction. It can be in any a space-time point that's in the future, in the past, to the right, to the left, above, below. Anywhere around here, she can identify those points using a unique coordinate system that's adapted to this tetrad basis. And that coordinate system is going to be a very simple coordinate system that we're going to take advantage of for our proof describing our interpretation of the curvature